Hello, today's notes are day 3 of graphing rational functions. We're going to get right into it with a definition for a removable discontinuity, which is also sometimes called a hole. Please pause the video now to copy it down, start processing what this might mean, and then come back and we'll talk about it. Okay, so I would like to focus in on discontinuity first. We have two types of functions. Can either be continuous, where there are no breaks or gaps, or in other words, I can draw it without ever lifting up my pen or my pencil. Now what goes on in the middle, it could be as complicated as this, but it's still continuous because I was able to draw it without lifting up my pen. Okay, but then discontinuous is, yep, you guessed it, where there is a break or a hole in it. And we've already talked about one of them. You may already be thinking about it, and that's the vertical asymptote. For example, I'm going to go ahead and draw myself a horizontal asymptote so it looks like what we did yesterday. A little familiar. We had something where I could start graphing, but then at this point I would reach a point where I had to lift my pen, come to the other side, either starting from here or up here, and let's do this one, before continuing on. Now, today we're going to talk about a new type of discontinuity where it's literally going to be a hole in our graph, and we'll see what that looks like later on in the examples, but just to give you a quick visual, there's going to be a point here where there's a little open circle, and at that point our function does not exist. Okay, I'm going to get rid of this so that we can get started. Ready and magic! Okay, now that we have an open space to work, we'll get started. Our first step is going to be to factor. I've written that step here. I've written that over here. I'm going to be putting our steps to this on the side for you to write down and have to reference. Today's lesson is going to be more clear why it's so important that our first step is always to factor. In this case, I'm going to factor out to x minus 4 and x plus 1 all over my x minus 4. Now, previously, like yesterday, when we looked at domain restrictions in the denominator, that indicated to us a vertical asymptote. Now, we're going to go into it with the same kind of idea, except this time there's a new possibility for this continuity, this hole. And the way that we can tell is because, as we stated in the definition, we have a factor up top that is also in the denominator. So we know from simplifying our expressions from before that we're going to be able to cancel these guys. That's what makes that discontinuity removable, because we can simplify our function to just be y equals x plus 1. We've literally removed that domain restriction from our function. Now, what that'll look like, as I said before, is a little open circle in our graph. Now, where is that hole, though? Well, we approach it the same way that you would a vertical asymptote. You go to the denominator, set that factor equal to 0, and solve for what x is, and x equals 4. So the step that we just took was to cancel, and then next, we took just that factor that we could cancel, set it equal to 0, and solved for x. Our last step is going to be to find the y value when x equals 4 in our graph. And the cool thing is that we have a simplified form that we can use. So plugging 4 into this equation, we just get that y equals 5. You can write this as a point, 4, 5. And that's it. That's our 4 simple steps. So now we just have to graph it. And I'm literally going to go over to my point 4, 5, and draw that open circle that we had talked about before. Now here, if you still had a rational function, you could use radii to extract more information. But notice that when we reduced it, we just got a linear function, and we know how to graph those. My intercept is going to be at 1. My slope is going to be 1, so I can graph a few points to help me out. And I know that it's going to continue on both sides of this hole, because what we're doing is basically it's the same graph that we would normally do, except that we have this hole in that place. Okay, let's look at some more examples. Going on with number 2, follow along with your list that I hope you wrote down. If not, go back and look at it. But first step, factor. Factoring out of 5, I get an x minus 3 in the top, x minus 3 in the bottom. Here are my 2 factors that are going to be able to cancel. That's my second step, cancel them. Then figure out where that hole is by setting that factor equal to 0, solving for x, and, oh, I didn't write my simplified form, but it's left over right here, y equals 5. Here there's nothing to plug x into. My y's are always going to be 5, so I already have my point. No need for step 4. So I go over to 3, 5, draw my open circle, and I know that y equals 5 is just a horizontal line, and so I fill that in. This way. Fantastic. Now it's up to you if you would like to first draw this function, and if you're using pencil, then erase where that hole is and fill it in afterwards. The order doesn't matter. However you'd like to think about it. Let's move on to number 3. See, isn't this quick? Okay, so here we are all factored, but we do see that we can cancel something. I can rewrite to make it a little clearer what's going on. My x cubed as x multiplied by itself 3 times, and an x in the bottom. So what's going to cancel is this x and one of the x's up top, leaving me with just x squared. To find out where our hole was, moving on to our third step, is just set x equals 0. There's nothing to solve for here. All we have to do is plug it back in to our simplified form to find y, and 0 squared is also 0. I have both my x and y. There are no other factors that I need to consider, so my only hole is at 0, 0. And I just noticed that there's a spot over here for us to keep that information, so if you'd like to go back to 1 and 2 and fix that to be more organized, please do. Now that just means I'm going to have my open circle there at the origin, 0.0, 0. Now x squared, I know how to graph this already, so I don't need to go to radii. I'm just going to plot myself as many points as I can on this graph so that I can be as accurate as possible. I'm just going through my squares. And looks like that's the last one I'll be able to fit on this graph. So the last thing I need to do is connect the points. Now notice that with these graphs that we've been working with previously, such as quadratics and linear functions, I like you to be as precise as possible when you're graphing these. The graphs that we did yesterday that had the horizontal and vertical asymptotes, those I'm okay with just the general shape, but do try to be careful with these, especially on quizzes and tests, to get full credit. Okay, let's take a look at a harder example with number 4. With number 4, again, I start at my first step, which is to factor. I'm fully factored in my numerator, so I'll just copy that down. Then in my denominator, I think to myself, what can multiply to give me -2 and add to a +1? Well, that's just going to be x plus 2 on this side and x minus 1, multiplying again -2, but 2 minus 1 gives me +1. Perfect. Please check your answer when you're factoring. It's really quick, and then it'll prevent you from losing more points later on. I just redistribute it quickly in my head and make sure that I get this polynomial when I distribute and multiply these two together again. Alright, our next step is to cancel, and I notice that I have the same factor of x plus 2 on the top and the bottom, right here, and I'm able to cancel those. Step 3 is to start to figure out where a hole is by going to that factor, setting it equal to 0, and solving for x. Here I get that x will equal -2. Final step in finding our hole is to go back to our simplified form. So I have not written that out nice and neatly, but we can go back and do it now. Our y is going to equal, well, I've canceled out the x plus 2, So in the top, I'm just left with 1, not 0. And in my denominator, it's x minus 1. Why? Because here, what do we have? We have the same thing on top or the same thing on bottom. What would you say 2 over 2 is equal to? Yep, that's right, 1, or 1 over 1. That's why when we cancel these out, we're still left with a 1 on top. There's also a 1 multiplying here, but 1 times x minus 1 is just x minus 1. Quick note and a reminder. Okay, so solving for y, we plug that into our equation, and we're looking at 1 over negative 2 minus 1 equals 1 over negative 3, or just negative 1/3. Our whole then is going to be at negative 2, negative 1/3. Now for the first time in these notes, we do still have a rational equation even after we've simplified. And so I am now going to use radi to help me graph the rest of the function. First thing I'm going to do is go over and fill in my hole though, and it'll be a little tough for me to be precise with this, but it's a little under the x-axis over at x negative 2. Let's see where our roots are. Well, I go to my simplified form at this point, not our original, because we can gather information more easily from this simplified form. And I set my numerator equal to 0. Oh, but I can't. 1 cannot equal 0, so that indicates to me that there are no roots. Next thing I want to look for is my vertical asymptotes. So I set my denominator equal to 0. X minus 1 is going to equal to 0, indicating to me that I have a vertical asymptote at x equals 1. Let's draw it in. X equals 1, drawing my asymptote with a dotted line. T is for two things, tangent or togetherness. By the way, if you're still not really comfortable with radi or you'd like to have a reference out for you, please take out your foldable about radi and follow along. So we're looking for multiplicities of 2, and we do not have any in this case. So we write none, and that'll help us finish graphing our equation later on. Looking on to end behavior, we want to go to our highest degree and take a look at those degree values. Now up here I have a 1, but I still have a degree because I could have written x to the 0 here. From our exponents unit, we know that x to the 0 is just 1, so I'm not changing anything. That just makes it a little bit more clear that we have a degree of 0 on the top, and on the bottom we have a degree of 1. That means that we have a bigger degree on the bottom, and remembering Bobo, we have that our horizontal asymptote is going to be at y equals 0. I'll go ahead and draw this in for us. Finally, our y-intercept, and that's when you plug in x equals 0 into your function. So going here, I'm going to say y equals 1 over 0 minus 1. That's 1 over negative 1, or just negative 1. Fantastic. So I'm going to intercept right here. Well, on to graphing, we have 2 points that our function is going to touch, and we have asymptotes on this side of the graph that we need to hug. So I know that I'm going to have to start down here and go up towards these 2 points to pass through that y-intercept, reach the hole, and then on the other side I'm going to continue on and hug that asymptote still. Now to figure out what's going on the right hand side of my asymptote, I could do one of 2 things. One, I could pick an x value over here, plug it in, and test where my y value is going to be, either positive or negative. Or I could save myself some time by remembering that I can get this information from t. There was no tangency and no togetherness. Togetherness is the one that's really going to help us because since this graph is going down on this side of the asymptote and we don't have togetherness, we need to be going in the opposite direction on the other side of the asymptote. And there I also hug my asymptotes. Number 5 and number 6 are going to be your homework problems, and they're for you to complete on your own. Now, to gain full credit for your notes tomorrow, I will be checking 5 and number 6, also for accuracy. So please make sure that you're taking this time, try it on your own. Number 5 is very similar to number 4, so there's your hint there. If you need help, go back to our video and see what we did in problem number 4. And number 6, I would like to note one thing before I let you practice. I have already gone ahead and shown the factoring for number 6. I'd like us to notice that in this case, we do not have any factors that can cancel on the top and the bottom. And so that means that we do not have any holes. We have none. Well, that means that this problem reduces to what we were seeing yesterday. So you'll just follow Rady and use this information to graph. You will not have any holes. That's your hint for that one. All right, good luck, and I'll see you tomorrow.